Hey everybody, it's spring 2022. This is Math 21, Introduction to Statistics at College of the Sequoias. Today we're starting chapter 5, the probability chapter. And we're going to get through 5.1 and 5.2 today. There's 5 sections. The first one is really the longest, and I had originally scheduled 5.1 through 5.3 today. I think a better breakdown is 5.1 and 5.2 today, and then 5.3 through 5.5 on Wednesday. So let's dive into it. So before we talk about probability, because there's something that's really closely related to it, let's recall what frequency is. And frequency was the number of events or number of occurrences of a specific event. Ooh, is it 2 R's? That looks funny. I think it's 2 R's. Number of occurrences of, let's call it an event E over the total number of events or people or, you know, when we got the frequency of how many people are left-handed, we would count how many, if we had 200 people and 12 of them said I'm left-handed, we would say 12 over 200. So that's frequency. And frequency is a measure of how often something occurred in the past. How often a specific event occurred during a unit of time. Like if we said how many people crossed through this intersection, or in a certain number of trials or events. That's frequency. This is historical data. Now, it doesn't have to be long in the history. It could have been just today, but it's happened in the past. That's where it differs from probability. Probability is the likelihood of an event happening in the future. Let's say the same thing, event E happening in the future. The outcome is unknown. As it hasn't happened yet. That's a little too much. But it looks the same. How do I want to put this? Another way of putting this, it's the long-term proportion and proportion is just like a fraction or a decimal, like we had with frequency, in which a certain outcome happens. In situations with short-term uncertainty. Again, Yeah, you have an eraser, just erase it, David. Because when you see probability, and you're going to go, if you've been doing your homework and you're up on frequency and relative frequency, it looks just like relative frequency or frequency. It looks and is calculated exactly like relative frequency. And that's why I brought up the difference. The frequency is what's happened in the past. We know the outcomes already happened. Probability is the likelihood or chance that it happens in the future. So common instruments we use to reflect this. Traditional instruments, the instruments of chance. What do you see when you go into a casino? Are any of you old enough to have been to a casino? I never know. Casinos have dice games like craps. Where they use 6-sided dice. Dice is plural for die. They have card games. Oops. Blackjack, poker. With a 52 card deck. Sometimes with 2 jokers. And you might see other things like bingo or Keno, but I'm not going to give examples of those there. I'm sure everyone's seen at least bingo on TV. But I do have some examples so I can show you pictures of decks. If you're not everyone here has used a deck of cards, has never used a deck of cards. It blew my mind when I asked that when I started teaching, and people like I asked after going through a deck of, using it in examples and finally noticing someone looked confused, had no idea what a deck of cards looks like. So this is a deck of cards. It comes in 4, there's 52 cards. There's 4 suits. A suit is the shape that appears on the cards. The top row here is diamonds. The next row here is called clubs. They look like 3-leaf flat clovers, but they're called clubs. Valentine's Day, everyone knows what the heart looks like. And the black upside down heart with a little thing sticking out is called a spade. Spade isn't a name for a shovel. This looks like the head on a spade shovel. So there's 4 suits, diamonds, clubs, hearts, and spades. They have different colors. Notice that the diamonds and the hearts are both red and the clubs and spades are both black. They go through cards from 1 to 10. The 1 is called the ace. That's why it has an A there. And then there's the face cards, Jack, Queen, King. They're called face cards because they have faces on them. And we'll use those an example or several examples throughout the day. And I'll come back and look at these pictures when we do it, when we talk about it. 6-sided dice. Hopefully you guys have used these, but they have a different number on each side: 1, 2, 3, 4, 5, and 6. Normally, numbers that add to 7 are on opposite sides of the dice. So that 6 on the top should have a 1 on the side that's on the back side, because 6 and 1 add to 7. It has 5 dots on top, which means there's 2 dots on bottom. Those add to 7. I can see the 3 is on the right, which means there should be a 4 on the left because those add to 7. 6-sided dice are numbered 1 through 6 on their sides. Those aren't the only types of dice that there are. There are several different shapes that can be tiled into a 3-dimensional figure. 4-sided dice have 4 sides. They're like pyramids. Here's the 6-sided dice. These two are both 10-sided dice. They tend to have 5 around one side and 5 around the other, and the way they land is how you read them. The 8-sided die, where my cursor is now, is like a pyramid that's got a square base. So there's 4 triangles going up to the point, and then you stick the 2 bases together. The 12-sided die is this weird one that's got pentagons along the edges, the shapes of the edges. And the 20-sided die has triangle-shaped edges, but there's 20 different sides. In all of them, you read them with the number that's generally on the top. The only difference that tends to ever be is on the 4-sided die. Here it is exactly as it is. You probably can't see it, but on this right side, it has a 3 on the top as well. All the way around the top of the pyramid on the 4-sided, it shows 3s. That's the number it rolls. Sometimes it doesn't do the points. It does it along the edges, and then it's the number on the bottom on all sides. But they all represent a way of generating random chance. So go back over to our stuff. So let's do just some examples. I could roll a 6-sided die. Which I have near me somewhere. Or I take all my D&D dice in the other room. That would be great. There we go. So nice little die. I don't know if you guys can see me in the camera. I'm going to roll it. And I got a 6 to show. So my 1 dot toss of a die is a 6. So for right now, I could say I am out of one event, one total event, I've got 1 6, which is 1. It's not even a decimal. It's exactly 1. But if I didn't get any 5s or 4s or 3s or 2s or 1s. So like if I look at 3s, I got 0 3s out of 1 toss. And so that's a 0. I could throw a few more. All right, so adding to the 6 I had before, let me just do a little tally real quick to give you the idea of how this works. The numbers on top are the numbers I could roll. I had 1 6. I have 3 1s here. This is dumb. I didn't do that well. So let's just do hashtag marks. I have a 4 and I have a 5. So the total number of outcomes here, total rolls or trials, is 6. Maybe I should roll 2 more. I got another 5 and I got another 6. So I've got 8 trials or 8 outcomes. Oh, that works. So if I start looking at my relative frequency, the relative frequency of a 1 is I had 3 rolls over 8 which is 0.375. Whereas my relative frequency for 2 and 3 is both 0. Four is 1/8, which is 0.125. And then 5 and 6 are identical. They're both at 1/4 right now, or 2/8. And 2/8 is 0.25. These are relative frequencies. These do not represent the probability of me rolling a 1, 2, 3, 4, 5, or 6. So that's how relative frequencies differ from probability. The way they're connected is with enough trials, the short-term relativity or short-term relative frequency approaches the long-term probability. And let's take a look at how that works. Let's see if I can find a good dice simulator. How does this work? So, oh, that's not enough dice. Let's choose one that's got a lot of dice. Ooh, dice roll random might. Nope. Simulator. Let's throw 1,200 dice. Let's see if that works. Hit enter or send. Nope. Just calculate it. All dice. A 1. I don't know how to make this thing work. They made it a pain in the butt. Where's one that works really well? So let me just click this a bunch of times. Can I turn auto on? There we go. All right. So I've got 360 rolls in my simulator. And I'm making a table. I'll switch back over to the table in a second. On my rolls and outcomes. Rolls are 1, 2, 3, 4, 5, or 6. And the numbers on top are my outcomes. And let's see if I can move this chart back. I can't. I'm going to reset the display. I want you to watch this graph right here. There's relative frequency for the event 6. I'm going to turn on automatic rolling again and watch what happens. It shoots up to 30%. It's at 20%. It goes back up, dips down to 15%. It's back up to 20%. It's kind of like all over the place. It dips back down. Now it's going back up a little bit. And the further we go, the more number of rolls. We're calculating the relative frequency. That denominator gets higher and higher and higher. And it starts to flatline a bit. I'm going to let it go for a little while. Because right now it's still running a little high. It hasn't hit its actual appropriate. And it's getting to where we'll go to about 1,000. It's starting to flatline, isn't it? It's dipping up, it's dipping back down, it's fluctuating. It's actually running a little bit low right now. It's great. Two more rolls. Okay, so this chart here, it says 16.66%. The reason why that number's on there is that's the expected probability. And when we noted that it was up at like 30% in the beginning, it dropped to 25. It's now below 16.66, but it's starting to change a little bit. This shows a couple of things. This idea that the number of trials as the trials go up. Oops, someone chatted. The D100 is a lame die. I didn't put it on there. The D100 has 100 sides, but they're so small, it's more like rolling a marble. That's a good question. I just saw it. So let's go back over to our. Actually, it's on that same tab. There we go. So we saw for 6, it shot up to 30%, was down like this, and it starts to flatline. This is called the law of large numbers. Law of large numbers. And I actually said what it was above hand. With enough trials, the short-term relative frequency approaches the long-term probability. And we'll go over how you calculate long-term probability for dice rolls in a little bit. But I can tell you for dice, on any given one side, it's 16.66% or 6.67% for any given side. And we saw by only throwing a few, like I threw a few up here, I was nowhere near 16.66%. But on this, they started to get closer and closer to 16.66. In fact, we could look at the 59, right? Let's look at the 5 right here. How close was the 5? I apparently need to clean my room better. My office is getting cluttered and I can't even find the calculator I have sitting out. So there was 360 trials. 59 of them were 5s. 59 divided by 360 is 0.16389 if I round. But that's how the law of large numbers works. The more outcome, or more trials, like in this case, the number of dice we roll, the more relative frequency approaches the actual probability. And we saw that on the simulator as it ran. Note up here a couple things. When I rolled to start off with, the 6, my first roll here, I had a 6, and I got a 1. And everything else was a 0. So that gives us some important information about probability. The rules of probability are for, let's see, the probability of event E occurring we will call this P with parentheses. That should look like a better E. Let's make it a regular E like that. We put probability like this. P on the outside represents probability. And the letter we put on the inside represents the event. Probability event E. For probability event E, it's always 0 is always less than it, and it's always less than 1. Where a probability of an impossible event is 0, like rolling a 7 on a 6-sided die. The probability of an impossible event is 0, and the probability of a guaranteed event in this case, rolling a 1 through 6 is 1. Any other possible outcome is between that. Okay. Some words they'll use is things like sample space. The sample space is usually called S. And S is the set of all possible outcomes. In the dice game, in using one die, the outcomes are, oops, that should look like curly braces, but it does not. A 1, a 2, a 3, a 4, a 5, a 6. That's S. So it's just all the possible outcomes, and it has to list them all. These are the individual outcomes. And events are a collection of one or more outcomes. Like we could just say rolling a 6 is an outcome, is an event. It's also a specific outcome. It happens to be both. But I don't have to just limit to numbers. I could say rolling an even number is an event. Or rolling an odd. Or rolling the lower half. One of the lower half. Which would be like 1, 2, or 3. So any of these can be events. And the way you want to name events is we generally use letters for events. Because we don't want to write out a lot unless the word's short. Like 6 is a short word. I could say probability. I don't want to write the number 6 like that because that's confusing. Maybe spell the word 6. Here I could say probability of even, or I could say probability even with an E because I'm just using the first letter. Maybe doing it with an odd, I would say probability odd or an O. Maybe for lower half, I'd say probability of lower half, use 2 letters. So that's how we do naming schemes and stuff like that. So one of the rules of probability I listed above. So I'll rehash that. So 0 is less than or equal to the probability of any given event E, which is less than 1. This says if we break it up into 2 ways, probability event E is greater than or equal to 0, and probability event E is less than or equal to 1. So no negative numbers, no negative probabilities, I should say. And no probability is greater than 1. And there's one other rule. For an event E or EI, they sometimes list it like this, EI, where I is a subscript denoting the outcome. So maybe I could say E1, 2, 3, 4, 5, or 6. The sum of the probabilities has to equal 1. Sum of all probabilities. for all outcomes, not events, but all outcomes. Which means I should change that. I should say for an outcome EI. Equals 1. And we've seen this symbol like that before, which means add shit up. This is sigma. The probability of EI equals 1. Those are the 2 rules of probability. And when we calculate it, or it's calculated like relative frequency. Total number of occurrences of E over the total number of total outcomes in the set, or total outcomes in sample space. And some, I know they show this sometimes. They'll put this N of E over N of S. And that's exactly what this means. N represents number. So N in parentheses E is the total number of occurrences of event E. And N of S means the total outcomes in the sample space. Oop, nope. Total. How do I want to say this? I want to change the way I worded this because it sounds more like relative frequency. Total number of ways E can occur, because it hasn't happened yet. Probability is it hasn't happened yet. Total number of ways E can occur. Now it's over total number of ways, which is our sample space. That's a little bit better. That rings more true. All right. So 2 ways of doing it. We got our classical method. Classical method for determining probability. So what must be true to do this? All outcomes must be equally likely. Not all events, all outcomes. So for rolling a die, the probability of rolling a 1 has to equal the probability of rolling a 2, has to equal the probability of rolling a 3, has to equal the probability of rolling a 4, has to equal the probability of rolling a 5. This has to equal the probability of rolling a 6. Which makes doing probability for the classical method fairly easy. Do it for 1 and you have it for all. probability for all. So this n of E over the n of S, that is the probability of E. And we're going to apply that here. Let's just do the probability of getting a 6. The probability of getting a 6 on a 6-sided die, there is only one way to roll a 6. Over 6 different possible outcomes. So getting rid of the words, we have 1 over 6. If you throw that in a calculator, 0.1666666666666, it keeps going. And if I want to write this as a percentage, as we often do as humans, math requires the decimal, but we like to look at this as a percentage. We move the decimal right twice, and I get 16.6666. It keeps going. %. And that's where they got the picture on the that's where they got the number on that die simulator. We can look at the probability of doing any in a deck of cards. It has 4 suits. Remember, hearts, diamonds, clubs, and spades. And each suit has 13, they're called ranks. The ranks are the letters or numbers on the card. We got A, 2, 3, 4, 5, 6, 7, 8, 9, 10. The face cards are called Jack, Queen, and King. Four times 13 is 52. There are 52 cards in a deck without jokers. So the probability of any given card let's say ace of spades for our example. There is 1 ace of spades in the deck. There are 52 cards. And 1 divided by 52 is 0.019230769. If I move the decimal right twice, it would go here, which would be 1.923%. If the probability of an event E is less than or equal to 0.05 or 5%, we say the event is unusual. That was an S and it came out as a line. The 5% is not a hard and fast rule. Sometimes we go lower, sometimes we go higher. but a general good rule of thumb is 5%. And the problems in the computer homework are going to assume that. They'll have you check for values that are below 0.05. So in this case, the probability of the ace of spades, which is 0.019, that is less than or equal to 0.05, which makes drawing the ace of spades, if I draw just one card, this is an unusual event. Now, to me, if it were even like 6% or 7%, it's going to feel like it doesn't happen very often. And I would still, in my head, say it's unusual, but we have to pick a number just to be consistent across everything. So we pick 5%. If you've played Texas Hold'em, oh my God, I mangled the word. In Texas Hold'em, you get 2 cards face down. Or picture down, where you see the number is called the face of the card. The probability of getting a pair, and these are called the pocket cards, pocket or hole cards. The probability of a pocket pair, whether it be aces, twos, threes, any of them, is 0.0588 or 5.88%, which makes this a greater than 0.05. So in terms of statistics, it's not unusual. Now, if you've ever played a Hold'em, it sure as hell feels unusual. But if you were going for like a specific pair, like a pocket pair of aces, sometimes called the pocket rockets. This is 0.00452 or 0.452%. So this is unusual. That's an N. There we go. That's the classical method, and that requires knowing what all the possible outcomes are, and that they all have to be equal. When we don't know that all outcomes are equally likely, or don't think all outcomes are equally likely, we determine probability through experimentation. And how that roughly works is you do it enough times that doing it one more time doesn't really change the outcome. Doesn't drastically change the probability. This is when the law of large numbers is kicked in. Has taken effect. And I'll show you an example. Give you a chance to write that. We're going to look at a fun case. We call this empirical probability. That's what it's called. And for us, we're going to look at a game called Pass the Pigs. When I do this class in person, I have about 20 or 30 pigs and we do it. But since we're doing it online, I'm just going to show you what Pass the Pigs look like. Oh, better ways to look at images. Okay, so you got a pig. On one side, you can see it has a dot. On the other side, the left side, it doesn't have a dot. And it can land in such a way that it's on all four of its feet, called a trotter. It can land on its back, which is called a razorback. It can land on where it's just straight nose plant. Neither ear is touching the ground. That's called a snouter. Or it can lie all cockeyed like this, where the one ear and the nose is hitting the ground and one foot is hitting the ground. And that's called a leaning jowler. Or it can land with the dot just straight up or the dot straight down. There's 6 outcomes. And if we look at this in Wikipedia, someone has, they are not even probability. And there's a way to score points based on how you do it. But someone went through, and I'm sure they did it with students to get more people to do it, through experimentation. This is what, I'm going to write these values down. So through experimentation, where the number of trials, it says, is 11,954. We have side with no dot coming in at 34.9%. Side with dot face up is 30.2%. Razorback, which is flat on its back, is 22.4%. Trotter is 8.8%. Snouter is 3.0%. And finally, we have the leaning jowler. Which I'm going to call LJ. That is at a whopping 0.61%. So I pulled all the relative frequencies from the experimentation. And we're going to see if that's sufficient to work for the probability for the pigs. So I'm going to bring us back to the remote desktop. And you can see I wrote these all down. And let's see if the law of large numbers is kicked in. So if I convert this to a decimal, I got to move the decimal point left twice. It would be 0.0061. So I have the probability of leaning Jowler is 0.061. And I know that has to equal, remember, probability is number of events over number in the sample or the trials. I don't know the N of E, but I know the samples is 11,954. This is a little bit of an algebra problem. If I multiply both sides by this 11,954, number of events that are leaning Jowlers equals 11,954 times 0.0061. I don't have enough zeros over there. And what is that? I am getting 72.9194. Let's say that's approximately 73. So they threw the pig 11,954 times and got only 73 leaning Jowlers. Has law of large numbers kicked in? The reason why I picked leaning Jowlers to test this on, because I can calculate the number of any of them doing this same process, multiplying the total, the 11,954, by their probability. I can figure out how many times they rolled each one. Has the law of large numbers kicked in? Well, let's pretend one more pig was thrown. Was tossed. And it was a leaning Jowler. Now my leaning Jowler count goes up to 74. And my sample size, the number of times I've tossed the pig, goes up to 11,955. Now, if I were to do the relative frequency again, I've got 74 divided by 11,955. (0.006189878). If I were to round it, I would say 0.062. And so my percentage is 0.0 or 0.62%. It has changed by 1/100th of a percent. That hasn't changed it. That's effectively not changing it. This is basically not changing it. So we can treat the relative frequencies calculated as the probabilities. So also in this chapter is something called probability models. And I'm going to draw the one for a die. So in one column, they list all the possible outcomes. And in the next column, they list the probability of said outcome. And each of these is 0. Well, I'm going to do the fraction. 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. That's effectively what a probability model is. It lists all outcomes with all probabilities, all the corresponding probabilities. And you can verify it's a probability model. We can verify it as a probability model. If it meets the rules of probability. And as a reminder, the rules were the probability of any given event is between 0 and 1, which means none are negative. None of them are negative. Check, 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 check. These are all positive. So, and they're all less than 1. 1/6 is less than 1. 1/6 is less than 1. 1/6 is less than 1. These are all 1/6. So that requirement's met. And the only other requirement was that they have to add up to 1. The sum of the probabilities has to equal 1. Well, what happens if I add 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6? As a reminder, when the denominators are all the same, you can use just one denominator and treat that as adding up the numerators, which in this case are all 1s. And that many 1s adds up to 6. 6 over 6 equals 1. So that condition is met. This is a probability model. They will ask you that on the homework. Verify this is a probability model. This is what they want you to do. Make sure they add up to 1. Make sure that none of them are negative, and make sure that none of them are greater than 1. Sometimes they'll have all of them but one number. They'll have the probabilities for 5 of the 6 outcomes and ask what does the probability have to be for the missing one for it to be a model. And you just got to figure out what number you got to put in there to add up to equal 1. The thing I did with the pigs, the leaning jowlers, to calculate how many leaning jowlers they threw, they'll also ask you questions like that. They might say, uh, 400 people responded to the question, are you right or left-handed? or both, ambidextrous, where 44 of them nope, they don't tell you the number. That's exactly where it's trying to go. So I'll pick a different number. Where the probability of being left-handed was 0.13. How many people said they were left-handed? This is where we're using that probability of E equals N over E equals N of E over N over at or N parentheses S. And I know 0.13 is the probability of left-handed. I don't know the number of left-handed people, but I know the total number of people asked. And if I multiply both sides by that 400, the 400 goes away on the right, and I'm left with the number of left-handed people equals 400 times 0.13, which is 52. So 52 people said they were left-handed. Okay. They might ask you stuff related to a deck of cards. What is the probability that a random card drawn is a diamond? Or they could say, that's like part A. Part B is probability of an 8. And if you need to look at them, at a picture of a deck of cards, if you're not familiar with them, you can do it. And I'll skip back over to our picture of a deck of cards. So the probability of a diamond, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds. And there are a total of 52 cards. And while I'm here, I can do the eights. The probability of yelling an 8, there is 1, 2, 3, 4 8s. So the probability of an 8. There's 4 8s out of 52 cards. So if I go back over to my desktop, I wrote those things down, and you just got to calculate them. 13 divided by 52. I don't know why I'm putting it in the calculator because I know the answer. This is 1/4 or 0.25. 452 simplifies to 1 over 13, which is, that one I don't have memorized, 0.0769. And there's some more decimal places, so depending on where they ask you to round, you round appropriately. The last thing in 5.1, we're still not done. We're gonna go the full 2 hours a day. is subjective probability. This is where experimentation doesn't work. And it's oh, what do I want to call this? It's entirely based on personal judgment. Meteorologists do it with the weather predictions. It's 15% likely to rain today after 4 o'clock. That kind of thing. They rely on their experience and what they've seen before and the conditions that are now. But coming up with a number is just they're making that shit up. Economists do it, like stock market predictions. They base their decisions on previous trends. They're not just guessing, but they're basing it on experience. So let's take a look at 5.2. They might ask you one question about that, so I thought I'd bring it up. 5.2 is on the addition rule and compliments. Not like, hey, you look nice today, but that kind of compliment, spelled with an E rather than an I. Have you all played Monopoly? Let's see. Gabe's played Monopoly. Anybody else? Have you all? I hope you all have.
Yeah.
So, what? Let's say you play Monopoly. Okay, so I'm going to use a Monopoly example. And this is going to be based on like a house rule. They're not official rules, but enough people use them that they're common, I should say. An example of a house rule is all fees and taxes go into a jackpot that you win if you land on free parking. So let's say you're on electric company. I think that's the one that's 808. You're on electric company. God, I hope that's the one that's 808. And you want free parking or doubles. Which is 8 spaces away. Or doubles, so you can go again. What is the probability of 8 or doubles? So in Monopoly, you roll 2 dice. So maybe let's look at a dice table. So if I wanted to roll an 8, the grid is telling me which ones are 8s. So I'm going to write them all down. The 8s. Let's see, the second row has got, if I roll a 2 and a 6, the third row is a 3 and a 5. The fourth row is 2 4s. The fifth row, I've got a 5 and a 3, which is different than the 3 and the 5. It's just a different, if we had a red die and a blue die, it just depends on which one has the 3 and which one has the 5. They are different outcomes. And the same thing with on row 6, the 6 and the 2. So I am writing them like this real quick. I'm writing the dice outcome like that. And I could do the doubles without going back to it. Doubles, the dice have to be identical, which is 1 1, 2 2, 3 3, 4 4, 5 5, or 6 6. I notice I've got 4 and 4 twice, so I can't really count it. So the number of outcomes that are 8 or doubles, I've got, let's see, I will use white here. I've got 1, 2, 3, 4, 5, 6, 7, 8. I've already counted the 4 and 4. I won't count it again. 9, 10. 10 outcomes. We saw from the table, it was a 6 by 6 table. Six by 6 table had 36 outcomes. So the probability of an 8 or doubles is 10 over 36. And I'm just going to leave it as that. I don't need to know the exact decimal. I think that's good enough for the example. How does this relate to doing them individually? To probability of 8 or probability of double? Well, I could do the probability of 8. There was 5 different outcomes, right? 1, 2, 3, 4, 5 outcomes. So 5 over 36. And if I do the probability doubles, I've got 1, 2, 3, 4, 5, 6. 6 over 36, which I know simplifies, but I'm not going to simplify them. So if I added those two, probability of 8 plus probability of doubles, I've got 5 over 36 plus 6 over 36. We add the numerators because the denominator is the same. And I get 11 over 36, which is, damn it, it's getting moody now. It's getting hot to the touch. No, not yet. This is one larger on top. And it just so happens to be that 4 over 4. It occurred twice. It was counted twice. So if I subtract the overlap, I have probability of 8s plus probability of doubles minus the probability of it being an 8 and a double. I get 5 over 36 plus 6 over 36. Oops. Minus 1 over 36, which gets me 10 over 36. It's just randomly doing its own shit now. There we go. This is a general rule. Let's apply this. Let's make this events E and F. For events E and F, the probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. This is called the general addition rule for probability. What if I had wanted 7 or doubles? We already did this, the doubles. So the outcomes for a 7 are 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. There are, 6 outcomes. If I apply that general rule here, probability of 7 or doubles equals the probability of a 7 plus the probability of doubles minus the probability of 7 and doubles. This was 6 over 36. This is 6 over 36. Is there any overlap between rolling a 7 and rolling doubles? No, correct. No. And we can see that from our outcomes right here. None of these are doubles. No doubles. So that's kind of like minus 0 over 36, or we don't even need to do it. 6 plus 6 is 12 over 36. When two events have no overlap, we say they are mutually exclusive or disjoint. which simplifies the general addition formula for disjoint F's, E and E and F. Probability of E or F is just probability of E plus the probability of F. So it's a simplified form. It's worth noting. What are you doing, computer? It's worth noting the general one always works. And that's the one with minus probability of E and F. Final category or final topic is complements. When two events are mutually exclusive, and their probabilities add to 1, they are said to be complements. And I'm going to go back to the deck of cards thing for this one because I want to point out how it sometimes it's one way of looking at it. Recall for cards, we have hearts, which I'm just going to call an H, diamonds, clubs, and spades for suits, 4 suits. So I'm using the first letter of the word. Now, in this case, the probability of a heart getting is the same as getting a probability of a diamond, which is the same as the probability of getting a club, which is the same as the probability of getting a spade, which is 1/4. Or I could look at it like this. That's one way of dividing up the cards. Or I could say, break the cards up into 2 types. Or 2 groups. Heart or not a heart. Or no heart. Let's call it no heart. Like that first girlfriend you ever had. No, I'm kidding. So in this case, the probability of a heart is still 1/4. The probability of not a heart or no heart is really the probability of a diamond or club or spade. Ooh, I'm combining in the general addition bit, which is the same thing as probability of diamond plus probability of club plus probability of spade minus any overlap, which there are none. They're all identical, are all different. 1/4 plus 1/4 plus 1/4 is 3/4. So the probability of a heart plus the probability of not a heart equals 1/4 plus 3/4, which equals 1. Heart and no heart, let's just call it NH to shorten it, are complements. And they will write it like this. They use, it looks like an exponent C. The complement of heart, written like that, is no heart. And the complement of no heart is heart. So I could rewrite this up here as the probability of H plus the probability of H complement. I'm substituting this in for there, equals 1. And generally they do it with E's. They'll say probability of E plus the probability of E complement. You'll see it's the same thing as 1. But notice if I solve for the complement one, if I subtract probability of E from both sides, doing some beginning algebra, it may have been a little while for you, so hopefully this rings a bell. How to move stuff over is subtraction. The probability of the event complement is the same as 1 minus the probability of the event. This is the complement rule. Or another variation of it. This is actually the complement rule as well. The two complements have to add up to 1. Or we can rewrite it like that. Where this comes in really, 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 really handy. Check this out. It's like magic here. You're going to think it's even more magic when we start doing 5.3, 5.4. Well, 5.3 and 5.4. Example. I have 30 students. I don't, but let's say I do. Oh, fuck it. Let's say I have 120 students. I have 117 students this semester in stats. That's true. Now, I don't know if the following is true. I'm going to say 62 of them are boys, are male, and 45, nope, and 55 are female. Let's just go with birth gender. I know not everybody identifies as one of the two traditional genders, but let's just go with it because it makes this a little bit simpler. I picked 4 students. At random. What is the probability that at least one is a girl? That's my question right now. Okay, so what are my outcomes, possible outcomes? Possible outcomes in terms of girls. My sample space, my sample set, I could choose 0, 1, 2, 3, 4. I can tell you right now, these are a pain in the ass. Zero and 4 are a little bit easier. But when we do 5.3, you're going to see just how much of a pain in the ass that is. Calculating those out is a real pain in the ass, because let's look at just doing 2 boys. The first 2 could be boys, the first 2 or the last 2 could be girls. And the probability changes based on how many each are left when I pick each person. Or the first and third could be boys, or the first and fourth could be boys, or the middle 2 could be boys. There's a lot of ways it could come out, and that's just doing the 2. But the question asks at least 2, or at least 1, at least 1. At least 1 is 1 through 4. So this is actually it reduces my sample space to 0 or at least 1. And at least 1 is a pain in the ass to calculate. 0 is not. Probability of 0 girls, which is all boys, right? I have the probability of all boys plus the probability of the complement, not all boys, equals 1. I want this value, not all boys is at least 1. So the probability of at least 1 girl, which is not all boys, equals 1 minus the probability of all boys. And when we start doing 5.3, this is easy to calculate. This is torturous. Torturous. There we go. And that's kind of it for 5.2, which is good because we are done 5 minutes early. On Wednesday, we'll do 5.3 through 5.5. This took a little bit longer because a lot of people are uncomfortable with probability. I actually think it's, once you really understand it, it's probably the easiest section to at least relate to real life. Randomly drawing things is pretty easy to do. Imagine. That's it for today's lecture. Is there any questions? If not, I will see you guys on Wednesday, and I'll hit stop recording.